Hey guys, they're going to talk about conformance control using nanoparticles. Our advisors are Dr. Richard Hughes and Carson Thompson. I'm Spencer King.
Shelby Hedgepeth.
Adam Ali.
Cora Rosales.
And we are Team 25.
Okay, so conformance control using nanoparticles. Let's talk about what is conformance control. It's the reduction of water cut during production after a water flood has been implemented as a form of secondary recovery in that reservoir. Some goals for conformance control is to increase the sweep efficiency of the reservoir by forcing the water through low perm zones instead of just letting it take the path of least resistance through a high perm zone. The goal is to produce more oil and less water because you're pushing out the low perm oil that would have normally just stayed in the reservoir. And the reason that we should care about this is that our industry is spending $40 billion per year just on water disposal costs. So if we can keep it in the reservoir longer and push out more oil, that means we are producing less water and therefore spending less money on disposing it.
So the simulator we've been working with is called NPSL, or streamline-based nanoparticle simulation. It was developed in conjunction with ULL and LSU. The main developer of the software has been Wang. He's been our second-year advisor this semester, extremely helpful. And the main benefit of this simulator is that it allows us to understand encapsulated nanoparticles as they propagate through the reservoir. And it's extremely important to our project because conformance control, what we're looking for is a way to clog those high perm zones and force the water into these zones. For us, that's using HPAM and chromium coming together to form a weak shell system, which forms that high viscous fluid that clogs the formation and forces the water on the outsides. And the neat thing about NPSL is that it can generate results not only in terms of grid blocks like CMG or others, but also in terms of streamline. And this is what's called ParaView. It is our visualization software, and this is actually a image of what a streamlined simulation looks like. So all of these individual streaks are the particles' path through the reservoir. And this TOF means time of flight. And this is the beginning, this is the end, the blue and red respectively. And so the injection here of the particles, and you can see all the paths as they travel through the reservoir to the production sites. So it's actually a 5-spot pattern. So you have injection here, production, 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 and you can see each of these kind of pieces of the pattern from this model. And there are three major parts of the simulator itself. One is the Excel interface, which allows us to change parameters to change things we're looking at, and also to create input files for the executable. Now, the best way to describe the executable is you have been in 4056, and you're familiar with CMG. It's the black box, the IMEX piece that you can see like the time steps as it goes by. But if you're not familiar, it's basically a program that runs in the background and takes input files, runs algorithms on those input files to create output files. Those output files go into ParaView, which is our data visualization, and allows us to actually analyze those files. This is the main page of our Excel interface, and it allows us to change various parameters. There are also 4 other tabs on the bottom you can't see with more parameters we can change. But here are some examples of some of the stuff that is variable. The Create Files button allows us to create those input files for the executable, so that we can create the output files and analyze the results.
Okay, so far we've run some simulations and come across some problems. One of them being we might have possibly found a bug. Another thing being the choosing of our reservoir. So initially, when we first started, we went with a piece of the SPE 10B grid block, which was about 90,000 grids. However, the simulations took too long in this one, and another factor was that we couldn't explain what was happening, as this reservoir is too heterogeneous. Therefore, we decided to make a new conceptual homogeneous reservoir. The first one that we started with was an alternate model where we had 5 layers. The red ones being 1,000 millidarcies and the blue ones being 200 millidarcies. However, in this reservoir, since there's such a drastic change in permeability, the math started being too funny. Therefore, we decided to make a second reservoir. This is our second reservoir, our second ideal reservoir, where our lower layer was 200 millidarcies and our top layer being 1,000 millidarcy. And as we go up, there was a change in 200 millidarcy. So we ran some simulations in this one, and as you can see in the top picture, we injected HPAM, and after the chromium busted, weak gel was formed. This weak gel should have resulted in a change in permeability. And if we look at this, also this picture denotes a slice of the reservoir. As you can see, since there has been a change in since there have been a weak gel formed, there should have been a change in permeability here. However, we do not observe that, so that's why we think there might be a bug with the system. Once that bug has been fixed by Ben, the creator of the simulator, our next step will be doing a sensitivity analysis. As so far, we can think of these are the factors that we think might affect how we can maximize polymer flooding using nanoparticles. And these are like mass fraction of chromium, adsorption and desorption of that weak gel, injection parameters, like where we should inject the wells, what should be the injection rate, the burst time, when should the chromium be released and that weak gel form, and lastly, the concentration of the weak gels and HPAM.
Okay, so when we met with our advisors, we spoke to them about the bugs that we possibly hit or whatnot, and what we were encountering with not being able, like Adam said, we had to keep changing our models. So they recommended that we make a new model, which is kind of in the form of 2D for investigating the fractured zones, because it's kind of the hot topic in the industry right now, and it's going to give us a more definitive results that we can look at. They also, when we spoke to them, they reinforced that we should know the background of the simulator, meaning that we shouldn't just be plugging in numbers to change and just hope that we get the results. We need to actually understand what we're doing. For example, like Adam spoke of with the absorption and desorption, we need to know what happens to the free-flowing polymers that are flowing through when the polymers that stick to the wall through absorption stick to the wall. Like, what happens to those polymers? How are they affected? What happens to the reservoir? And just the entire background of it. This also, whenever we met with them, they helped us understand the reasoning as to why we may have a bug, which the bug was result into no change in permeability. They gave us background on what we should do and what we should change. So this is the model that they recommended that we use. So basically what's going to happen here is we're going to have an injecting well right here in the center, and we're going to have a producer on each corner here. So what we want to happen whenever we inject polymers is for it to push the water and come out this way, which meaning this is the most permeable zone, as you can tell from the scale. We want the water to come across here to push out and come through the thief zones to enhance the recovery of our oil. So our project success so far this semester is we finally have our own computer set up in the graduate lab. Ben is now here at LSU, which is great for us because when we have a problem, we can just walk over to his office and he'll fix it right away. We are all now proficient in NPSL. We understand what each variable is and how to change it and the background of each variable. And like we said, we possibly found the first bug in the simulator, which is going to help Ben make the simulator better and work properly.
Okay, so we'll be measuring success of our simulation in a couple of different ways. The first is that we're going to produce the highest results we can through trial and error of sensitive analysis using the last ideal reservoir and our new one. We're also going to compare the ultimate recovery of a polymer flood using NPSL to the ultimate recovery of a polymer flood using CMG. This is just to show how our simulator varies or is similar to the ones accepted today and most common in the industry. Our third way is that we're going to use those sensitive analysis results I talked about earlier to perform a full field nanoparticle flood using the SBE-10B. This simulates the most real-life application of nanoparticle use in a field. Okay, so the project management aspect of our project is we've been using the application called Asana to communicate with each other, to share files. We can assign due dates, and we can also assign to certain people. We can make comments. It's basically just one interface for everyone, and it's a centralized thing, and it's great. And this is our Gantt chart, and this is basically a timeline of the whole project. We started in August, and we have made plans all the way up to April 26th. We've been a little behind at some places and a little ahead in others, but it's been a really great tool to keep us on track with our main goals. And that's all. So thank y'all so much.
Thanks.
Thank you.
Thank you.